Homochirality describes a geometric property of some materials that are composed of chiral units. Chiral refers to non-superimposable 3D forms that are mirror images of one another, as are left and right hands. A substance is said to be homochiral if all the constituent units are molecules of the same chiral form. In biology, homochirality is a common property of amino acids and sugars. The origin of this phenomenon is not clearly understood. It is unclear if homochirality has a purpose, however it appears to be a form of information storage. One suggestion is that it reduces entropy barriers in the formation of large organized molecules. It has been experimentally verified that amino acids form large aggregates in larger abundance from enantiomer substrates than from racemic ones. Homochirality is said to evolve in three distinct steps. Mirror symmetry breaking creates a minute enantiomer imbalance and is key to homochirality. Chiral amplification is a process of enantiomer enrichment, and chiral transmission allows the transfer of chirality of one set of molecules to another. It is also entirely possible that homochirality is simply a result of the natural auto-amplification process of life, that either the formation of life is preferring one chirality or the other was a chance rare event which happened to occur with the chiralities we observe, or that all chiralities of life emerged rapidly but due to catastrophic events and strong competition, the other unobserved chiral preferences were wiped out by the preponderance and metabolic enantiomer enrichment from their winning chirality choices. The emergence of chirality consensus as a natural auto-amplification process has been associated with the second law of thermodynamics, mirror symmetry breaking. Known mechanisms for the production of non-racemic mixtures from racemic starting materials include asymmetric physical laws, such as the electroweak interaction, asymmetric environments, such as those caused by circularly polarized light, quartz crystals, or the Earth's rotation, and statistical fluctuations during racemic synthesis. Once established, chirality would be selected for. A small enantiomeric excess can be amplified into a large one by asymmetric autocatalysis, such as in the SOAI reaction. In asymmetric autocatalysis, the catalyst is a chiral molecule, which means that a chiral molecule is catalyzing its own production. An initial enantiomeric excess, such as can be produced by polarized light, then allows the more abundant enantiomer to outcompete the other. One supposition is that the discovery of an enantiomer imbalance in molecules in the Murchison meteorite supports an extraterrestrial origin of homochirality. There is evidence for the existence of circularly polarized light originating from me scattering on aligned interstellar dust particles, which may trigger the formation of an enantiomeric excess within chiral material in space. Another speculation suggests that fundamental chirality of physical processes such as that of the beta decay leads to slightly different half-lives of biologically relevant molecules. Homochirality may also result from spontaneous absolute asymmetric synthesis. Chiral amplification. Laboratory experiments exist demonstrating how in certain autocatalytic reaction systems the presence of a small amount of reaction product with enantiomeric excess at the start of the reaction can result in a much larger enantiomeric excess at the end of the reaction. In the SOAI reaction, pyrimidine5-carbaldehyde is alkylated by diisopropyl zinc to the corresponding pyrimidal alcohol. Because the initial reaction product is also an effective catalyst, the reaction is autocatalytic. Another study concerns the proline-catalyzed aminoxylation of propionaldehyde by nitrosobenzene. In this system too, the presence of enantio-enriched catalyst drives the reaction towards one of the two possible optical isomers. Serine octamer clusters are also contenders. These clusters of 8 serine molecules appear in mass spectrometry with an unusual homochiral preference. However, there is no evidence that such clusters exist under non-ionizing conditions, and amino acid phase behavior is far more prebiotically relevant. The recent observation that partial sublimation of a 10% enantioenriched sample of leucine results in up to 82% enrichment in the sublimate shows that enantioenrichment of amino acids could occur in space. Partial sublimation processes can take place on the surface of meteors where large variations in temperature exist. This finding may have consequences for the development of the Mars Organic Detector scheduled for launch in 2013, which aims to recover trace amounts of amino acids from the Mars surface exactly by a sublimation technique. A high asymmetric amplification of the enantiomeric excess of sugars are also present in the amino acid catalyzed asymmetric formation of carbohydrates. One classic study involves an experiment that takes place in the laboratory, when sodium chlorate is allowed to crystallize from water and the collected crystals examined in a polarimeter. Each crystal turns out to be chiral in either the L form or the D form. In an ordinary experiment, the amount of L crystals collected equals the amount of D crystals. However, when the sodium chlorate solution is stirred during the crystallization process, the crystals are either exclusively L or exclusively D. In 32 consecutive crystallization experiments, 14 experiments deliver D crystals and 18 others L crystals. The explanation for this symmetry breaking is unclear, but is related to autocatalysis taking place in the nucleation process. In a related experiment, a crystal suspension of a racemic amino acid derivative continuously stirred results in a 100% crystal phase of one of the enantiomers because the enantiomeric pair is able to equilibrate in solution. Chiral transmission. Many strategies in asymmetric synthesis are built on chiral transmission. Especially important is the so-called organocatalysis of organic reactions by proline, for example in Minot reactions. Optical resolution in racemic amino acids. There exists no theory elucidating correlations among L amino acids. If one takes, for example, alanine, which has a small methyl group, and phenylalanine, which has a larger benzyl group, a simple question is in what aspect L-alanine resembles L-phenylalanine more than D-phenylalanine, and what kind of mechanism causes the selection of all L amino acids. Because it might be possible that alanine was L and phenylalanine was D. It was reported in 2004 that excess racemic D-L-asparagine, which spontaneously forms crystals of either isomer during recrystallization, induces asymmetric resolution of O coexisting racemic amino acids such as arginine, aspartic acid, glutamine, histidine, leucine, methionine, phenylalanine, serine, valine, tyrosine, and tryptophan. The enantiomeric excess E equals 100x of these amino acids was correlated almost linearly with that of the inducer, i.e., ASN. When recrystallizations from a mixture of 12 D-L amino acids and excess D-L-ASN were made, all amino acids with the same configuration with a SN were preferentially co-crystallized. It was incidental whether the enrichment took place in L or DASN, however, once the selection was made, the coexisting amino acid with the same configuration at the alpha carbon was preferentially involved because of thermodynamic stability in the crystal formation. The maximal E was reported to be 100%. Based on these results, it is proposed that a mixture of racemic amino acids causes spontaneous and effective optical resolution, even if asymmetric synthesis of a single amino acid does not occur without an aid of an optically active molecule. This is the first study elucidating reasonably the formation of chirality from racemic amino acids with experimental evidences. History. This term was introduced by Kelvin in 1904, the year that he published his Baltimore Lecture of 1884. Kelvin used the term homochirality as a relationship between two molecules, i.e., Two molecules are homochiral if they have the same chirality. Recently, however, homochiral has been used in the same sense as enantiomerically pure. This is permitted in some journals, its meaning changing into the preference of a process or system for a single optical isomer in a pair of isomers in these journals.